Hi everyone, I'm Clément Morand. I'm a PhD student at the Laboratoire Interdisciplinaire des Sciences du Numérique, just as Manuel said. And today I'm going to present you a talk on LLMs, AI, and deep learning impact, which was made with Anne-Laure Ligoza, which is my supervisor, and Aurélie Bugeaud, which work in Bordeaux. So, as was said in the beginning of the session, the information and communication technologies have a significant impact, and they are rising. According to the last figures by Mastodon and et al. At Ericsson, they evaluated ICT to consume 4% of the global energy consumption in 2020, and this is a 5% increase in emissions since 2015. So they are more optimistic than the evaluation by André, for instance, but still it doesn't stop increasing. So we need to have a discussion on that. And on machine learning, and especially, the size of model and the quantity of computation that's required to train state-of-the-art models has grown exponentially in the last 70 years. And nowadays, it accounts for more than 10% of Google's energy consumption, the machine learning-related activities. And as was also previously said, there are important emissions just from the energy consumption. So with the figure of more than 500 tons of CO2 equivalent to train GPT-3 once. So how do we go with measuring the impacts of deep learning methods? So after the work by Strobel et al. That showed the importance of deep learning impacts, there was a call for green AI research, exploring not only the traditional research ways, but also more sustainable ways. There were calls to evaluate models not only on their accuracy, on their raw performance, but also on their environmental sustainability aspects, so on their efficiency. And the green AI is now a research field in itself, and there are reviews of the field that exist. And to understand the impacts of AI, there were a lot of tools that were developed in two different categories of tools. There are the measuring tools that use system-based power meters, such as RAPL or NVML, that gives real-time information, real-time measures. And on the other side, there are the estimation tools, like the green algorithms that was presented by Loïc in the previous session. Both tools have their pros and cons, and they were surveyed to see the forces and the weaknesses of each one. The problem with these tools is that they only account for the energy consumption of the hardware, and they do not account for other types of impact than the carbon footprints. But the hardware also needs to be produced, also as an end of life, and there are also a lot of different impacts, just like in the water consumption, for instance. And a methodology for accounting for more impacts over the whole life cycle is called life cycle assessment. It's a standardized methodology with two ISO standards. There are two types of LCA that exist. So there is attributional LCA and consequential LCA. Attributional LCA looks at a fixed system. So for instance, given the current bus network, what is the impact of one bus travel? And the consequential LCA frameworks ask more macro changes, evolutions of the dynamics of the system. So it could focus on questions like, given the, what would change to the impacts of the current network if we were to add, I don't know, 2 new lines of buses or to have more frequent stops? And this methodology, so for attributional LCA, was proposed framework to adapt it to machine learning. And it was used to evaluate the carbon footprint of the Bloom model, which is an LLM developed by public research. And different works around the environmental impacts of AI have told us different things. So first off, it is important to not only account for the training phase, because it's unitarily important, but also the inference phase. For instance, at Facebook, the deployment of models, so the inferences when you query the models, represents more than 80% of their energy consumption. And it's also important to account for the embodied emissions, so the emissions that are due to the manufacturing of the hardware. And it has been shown that for smartphone, it's the almost totality of the impacts that are due to the manufacturing. And as Loic said in the previous talk, for data centers, since the servers are used much more, pretty much all of the time, the use phase becomes the dominant phase, but still the embedded impacts represent up to 30% of the total impacts over the life cycle. And to evaluate the production impacts, there have been a life cycle assessment of Dell servers that were published, and different studies on the key performance indicators for environmental performance of the data centers that were used to develop a tool for simplified LCAs of server by the Boa Vista Association in France. And we can use all of these information to define a better tool to account for as much as the impacts of computation as possible. So what is our aim? Our aim is to answer the question, what are the impacts of running a given program on a given hardware? And the idea is to have an estimation for one reason is to provide estimates before you engage with the work and to engage in a reflexive thinking. So what will my project require and emit? And do I really need to pursue this, or do the benefits not overcome the costs? So quick reminder on the life cycle of hardware, but on the life cycle in general. There are different phases of the life cycle of hardware. So first you need to extract raw materials, so you need to mine different ores. Then all of these materials are manufactured into the hardware you'll use. It's then transported to the facility where it will be used. And once it's not being used anymore, it's discarded. Maybe it's recycled or upcycled or burnt and we reuse some of the energy. But there are impacts of each phases, and each phases has different impacts. For instance, the raw material extraction requires to extract minerals from the earth. The use phase uses a lot of electricity, and each phase also emits different pollutants. So there is pollution in the soil, in the water, in the air. So in the air there are just CO2, but many others. There are toxicity. For instance, if you leave different metals in the water, it's toxic to human and to non-human life. And the objective is to account for as much as these different impacts as possible over the whole life cycle. And if we take a look at the current state of the art on the evaluation of computation, so I've given you a sample of a few tools that exist. As I said, they are focused on the energy consumption. So the dynamic energy consumption is just the energy of the hardware, and they also account for part of the energy of the infrastructure that runs this computation. But there are many elements that are missing. And if we combine this with the tool from Boa Vista, we see that we will be able to account for more life cycle phases and also for multiple impact categories. So the impacts that will be evaluated are first the abiotic resource depletion. So it deals with the mineral resource scarcity. It's measured in kilograms antimony equivalent. We also measured the primary energy demand. So not only the energy consumption that you buy, but also the energy that's needed to produce the electricity, and this over the whole life cycle. And obviously the global warming potential, so the carbon footprint. How does the tool work? So first you need to model and evaluate the impacts of producing the hardware. Then you need to attribute these producing emissions to a specific task. You also need then to evaluate the use phase, so the energy consumption and the energy consumption of the infrastructure. And then to make sense of these numbers, we want to put these into perspective. So first, how do we model the production impact? So we use a bottom-up approach. A machine is estimated to be a number of graphics cards, a number of CPUs, some memory, a motherboard, a storage, power supply units, casing, etc. And how do we model a graphics card? We model it as a GPU, so the integrated circuits, plus some amount of memory and a base, so the printed wiring board, the fans, and the connectors, etc. And we evaluate the impacts of each of these elements. So the GPU modeled by its size, by its area. We have an estimation of the impacts of producing 1 centimeter squared of a GPU. We also evaluate the impacts of memory by the quantity of memory. So we have a number for producing 1 gigabyte of memory. And for the base impact, we use results from the only known study that evaluates impacts of producing graphics cards, even if these are not graphics cards that are used in data center. They are much lower performances graphics card, but it's the only data we have. So in the end, the graphics card impacts are evaluated as the size of the GPU times the impact of producing 1 centimeter square of GPU, plus the size of the memory times the impact of producing 1 gigabyte of memory, plus the base impact. And to give an example, on the NVIDIA 100 graphics card with 80 gigabytes of memory, we estimate that to produce it requires the emission of 330 kilograms of CO2 equivalent. Then, once we have estimated the production impact, we need to attribute them to a specific task. For that, we use a linear attribution. And to do so, we want to multiply the manufacturing impact that we just calculated before, and multiply that by the ratio of the time that we're using it for our specific task over the whole lifespan. And to do that, we base ourselves on the information provided on the Jonzé cluster in France, which tells us that the servers are used 85% of the time and have a lifespan of 6 years. But this average use can be much lower in different cases, and the lifespan is also much lower in facilities which want to stay at the top of performance because hardware changes so frequently. And then we obtain the embodied impacts, which are the manufacturing impacts that we can attribute to our specific task. Then comes the modeling of the energy consumption. So it works just as Loïc presented. We multiply the duration of the computation by the power estimation of the different processing units. We add also a part for the memory usage. And once we've estimated this energy consumption for the specific hardware, we multiply this by something that we've called a dynamic ratio. So it's really close to what was presented before with the power usage efficiency, the PUE. But it also accounts not only for the cooling and the electricity transformation, but also for all the energy that's used for maintaining the devices on and distributing the computation, etc. So it's computed as the total energy consumption of the data center over the sum of the computations when running jobs. And on Jonzé, which has a PUE of 1.2, this figure comes up to 1.8 to show that it's not only the energy consumption of the cooling infrastructure, but also the infrastructure when it's in idle mode, when it's distributing computation, etc. And to get the final energy impact, we multiply the estimate of the total energy consumption by a factor. So for instance, the carbon intensity, if we want to give the carbon footprints. And once we have the figures, so we add the embodied impacts and the energy-related impacts. We have big figures or small figures, we don't know. We need to make sense of those. So typically, people present results with regards to, I don't know, how many kilometers in a typical car it takes or the flight duration. But we chose to use a different approach, which is to put these results in perspective with global sustainability scenarios, to understand that our solution might be better than the previous solution But if it's still way too high to be sustainable, then does it really make sense? So to do that, we use two different sustainability scenarios, which are the Paris Agreement to maintain the global warming by the end of the century, which fixes a limit of 2 tons of CO2 per person per year. And we also interest ourselves in the framework of the planetary boundaries, where if we want to stay sustainable and maintain the different equilibriums of the Earth systems, we need to not overpass the planetary boundaries, and it allows us to think not only on the carbon footprint, where we can see that the planetary boundaries on global warming is much lower than the 2 tons that are fixed by the Paris Agreement. So it's not containing, but it's stopping it. And it also allows to think of resource depletion or water consumption, etc. And so as I've said, we want to have not 1.45 kilometers in a passenger car, but have 1% year emissions, for instance. And if we look at results for training the Bloom model, training it once was estimated to require the emission of 59 tons of CO2 equivalent. So according to the Paris Agreement, this is the annual emission of 29 persons. And we can also see that for the abiotic resource depletion, so the mineral resource scarcity, which is mainly impacted by the manufacturing phase and the raw material extraction, it also accounts for the annual resource extraction of 38 persons. So it will not suffice to reduce the energy consumption. We also need to take into account the materiality of the hardware we use. So this tool was tested on different case studies. So first to evaluate the energy use modeling, to evaluate the hardware manufacturing modeling, and to evaluate the whole tool. And for the sake of time, I will only present 3 of them. So first, on the evaluation of the energy consumption modeling, so we tried to replicate results from the J et al. Paper that was mentioned by Loïc in the previous talk. And what we can see is that we are able to reproduce the exact results, but there was a database inconsistency in the fact that in the version that was used of the green algorithms tool, the value of the TDP, which is used to estimate the energy consumption of the GPUs, was lower than the actual TDP of the GPU that was used. So it explained the slight difference with the first bar, why it's a little bit lower. On the manufacturing impacts, we compared ourselves with the life cycle assessment estimates of Dell. We are the red bars and Dell are the blue bars. We can see on the leftmost, on the total columns that we are not that far. We are underestimating a little bit. And the decomposition by component shows that on some components we are underestimating a little bit, on other components we are overestimating a little bit. But in the end, it all compensates, and we have pretty good estimates. And if we look for the evaluation of a model over the whole life cycle of the hardware, so replicating the evaluation of the Bloom model, we can see that for the embedded emissions, so the emissions that are due to the hardware manufacturing, we estimate a little bit higher values. And this is because our methods for evaluating the impacts of producing GPUs yields much higher results than the value that was chosen, but they had to choose a value with no real knowledge, since NVIDIA does not provide information. On the dynamic energy, so the energy of the nodes when running the computation, we can see that we are really close. And on the infrastructure consumption, we are a little bit higher when we should have been exact match. And this is because the figures presented in the manuscript of the Bloom evaluation do not account for when the hardware is in idle mode, so when it's running but doesn't do anything. All of these experiments show us that our tool works, but they also show us a number of difficulties of measuring or evaluating impacts. So first, there is the question of data availability. Since manufacturers do not provide any information on the manufacturing impacts of the devices, for instance, or it can also be hard to obtain the energy consumption of Google devices like the TPUs. There are a lot of uncertainties, especially on the manufacturing impact, but also on the hardware lifespan or the hardware usage. And there are also difficulties of replicating results. We can see that even when papers provide these numbers, these figures, these evaluations they've made, it's also hard to give all the necessary information, so all the parameters they inputted to tools like the green logarithms tools to reproduce their exact results. And it's really difficult to compare different studies because they might have a scope mismatch. So, for instance, the Bloom analysis accounts for the embedded emission, while most studies do not account for it. So it might be hard to compare the figures produced on Bloom and on other models, since they do not account for the same thing. And one thing that we need to really be aware of is that it's really important to define the scope. So what will we take into account? And the objective of the measure before performing it. We need to know why do we measure and how do we measure. And this is because if we want to produce a key performance indicator, we might not require the highest certainty and the largest scope possible because we want to focus on what we can change at our scale. But if we are looking at accounting, for instance, we need the most precise possible and with the as wide a scope as possible. And all of what I've presented for now still provides an incomplete view. For instance, it does not at all account for the end of life of the hardware. And this is because there are very few data that are available on the end of life of hardware, since, for instance, more than 80% of global e-wastes are not documented. We don't know where they end up. And the lifecycle assessment databases do not properly model the ICT equipment end of life. For instance, they do not provide information on what happens when we let a GPU in a landfill. Also, we do not account for plenty of other localized environmental damages, so not only the resource extraction and the carbon footprint, but also the training AI uses a lot of water, for instance. And even if it does, data center does not use as much energy as, for instance, agriculture or other really water-intensive tasks, the water consumption of data center comes in competition with other uses, may they be by humans or also by non-humans, so like fish or plants downstream that might not have access to these water resources if we preempt them for data centers. And there are lots of pollution and toxicity to human and non-human life, especially in the mining phase where we need to use a lot of chemicals to extract the ores from the earth, and also in the end of life where there are, for instance, metals that are left untouched in the air or even in water, and this is really toxic. Yeah. There are direct social aspects of AI, so of the value chain of AI. There are the social consequences of mining. So for instance, in Congo, there has been an ongoing conflict since more than 20 years, in part over the access to the mining facilities of Congo, which produces more than 60% of the global cobalt ores. And the conditions in which the mining is done could not be as bad if there was not an armed conflict. And it's also a fuel of the conflict. There's the question of work in the data center, the quality of work in the data center, but also around the data center. What does it change to the local economic tissue to implement a data center? And there's the question of all the works that's required to produce an AI model, so the digital labor, the click workers in the Amazon Mechanical Turk, for instance, which have really bad working conditions. And there are also social aspects of AI use, so not only its production, but its use. So for instance, AI globalization might inter-climate activism because it allows for more mass surveillance. For instance, in China, it's really difficult to be an activist since the government has access to a lot of information on you and can recognize you in any streets, whatever you do. Large language models can reinforce existing discrimination, and tasks such as automatic gender recognition are harmful to trans people. So, in conclusion, it is necessary to account for more than just the carbon footprints, of more than just the energy consumption, of more than just AI training. There are environmental damages such as resource depletion, water consumption, and toxicity to human and non-human life that also should be addressed. The production and end of life of hardware also cause significant environmental damages, and we also need to consider the conception and deployment of models. And a last point that I want to emphasize on is that we cannot conceive a sustainable AI without conceiving a global sustainability scenario. A sustainable technology is not sustainable itself, only a society can be sustainable. Thanks for your attention.